In times of increasing water shortages globally, news of fresh water hosted in the ocean bottom have gathered widespread interest. Is such groundwater a hope for thirsty coastal cities? Does it pose a potential risk? For the last 5 decades, offshore freshened groundwater, also known as offshore groundwater, was discovered accidentally during drilling expeditions and has therefore been poorly investigated. Then, in 2013, a paper came out showing how offshore groundwater is a global phenomenon, with a total estimated volume to be equivalent to that of the Black Sea. This study inspired numerous projects on offshore groundwater, among which is MARCAN, a research project funded by the European Research Council between 2017 and 2022. A main outcome of the MARCAN project is a new methodology to systematically map offshore groundwater in unprecedented detail, which has become a trendsetter in the offshore quest for freshened water. Another surprising outcome is a new perspective on how offshore groundwater can trigger slope failure and thus shape the seafloor. To achieve these results, team leader Professor Aaron Mikalev has brought together scientists from all over the world because
Water scarcity is an international issue, and to address it, you need an international effort. Mostly because the best test sites to address our questions are found globally. There are people coming from different countries. So there's Malta, Germany, Iran, USA, Italy, Canada, China, France, Mexicans. But it's always increasing. I mean, the expertise comes unexpectedly from different areas. It's become like a small community. It's not like there haven't been people working on offshore groundwater before, but I've been able to enter a new community of geophysicists, especially working on electromagnetic data, and geochemists who have been working on offshore groundwater before. So I've discovered a new world of which I wasn't aware before, but also made new friends and working with new colleagues from these fields and others as well. So it's been a really enriching learning experience for me.
the MARCAN project took place in two phases. One concerning the quest for and detailed study of offshore groundwater. The second focusing on its role in seafloor evolution and hazard prediction. In the first phase, the MARCAN team developed a methodology for mapping and investigating offshore groundwater. To do this, they combined a number of geophysical, geochemical, and numerical modeling techniques. Mapping is performed by geophysics using different methods.
We have a number of techniques that we're using. The most important one is controlled source electromagnetics. So basically, we're using an electromagnetic signal to understand how the resistivity of the subsea floor changes. Now, imagine you have rocks or pores, so these spaces within the rocks, filled with salt water. So, salt water makes the whole material conductive, so the resistivity is low. However, if in that pore water there is fresh water, the resistivity will be much higher. Apart from that, we also have carried out some seismic reflection profiling, and that gives us an idea of the geological structure under the seafloor.
Hydrogeologists use numerical models to assess the volumes of offshore groundwater in continental margins and test different hypotheses for its emplacement. Whereas most numerical modeling approaches tend to be two-dimensional, the MARCAN team has developed and used three-dimensional models. Geochemists, in comparison to geophysicists and numerical modelers, study the composition of the offshore groundwater, either in the ocean bottom or seeping from it.
Here we did some water sampling and analysis, which is very important to understand the kind of fluid that is seeping out of the seafloor, what its origin is, and what its composition could tell us about how it ended up there. So this is a 5-liter plastic bottle basically that we lowered into the ocean until it got close to the seafloor. It's not very high tech, we got the Niskin bottle on board. We divided the water samples into two. One for a plastic bottle to look at the chemical composition, whether there are sodium, chloride, magnesium, etc. And the other one was for isotopes, because they will tell you whether the seepage Dissipating water could be groundwater, for example. If you look at the oxygen and hydrogen isotopes, it gives you an idea of what the origin of the groundwater could be.
Offshore groundwater has been derived from precipitation during the past ice ages when sea level was about 100 meters lower than today. It can occur as a fossil and isolated deposit. Such an offshore groundwater system would not be a sustainable resource to use. Alternatively, the groundwater may be connected to a terrestrial groundwater system, which is actively recharging the offshore groundwater. That would theoretically allow a sustainable use. For phase one of the MARCAN project, scientists explored two coastal areas, one being offshore Malta, Europe's most arid country, representing of carbonate aquifers that are common across the Mediterranean. The other was offshore New Zealand, representative of siliciclastic aquifers. Using the innovative methodology, the MARCAN team constrained the 3D geometry, extent, and characteristics of these offshore groundwater systems. They successfully identified 1 cubic kilometer of groundwater offshore Malta and more than 200 cubic kilometers of groundwater with a complex architecture offshore New Zealand.
Both systems actually comprise a combination of extensive fossil groundwater with smaller volumes of actively recharging groundwater that is derived from onshore systems, as was demonstrated by land surveys that we carried out with electromagnetic methods.
Eventually, a global literature review was carried out and a database compiled to assess the offshore groundwater globally, and the outcome is remarkable.
So, offshore groundwater actually has a global volume of 1 million cubic kilometers, which is enough to fill up the volume of the Black Sea twice. Offshore groundwater occurs in all continental margins, predominantly within 50 kilometers from the coast, down to a water depth of 100 meters, and most of it is actually fossil groundwater, which is hosted in siliciclastic aquifers.
After better understanding offshore groundwater systems in phase one, the MARCAN project moved on to the second phase to investigate how offshore groundwater can influence seafloor landscapes.
And then to address phase two, we actually went global because we looked at New Jersey and the Bahamas, as well as other sites.
And what they found out was surprising.
Offshore groundwater is a more important driver of seafloor change than initially thought. And we should start to take this into consideration both to reconstruct the environment in the past but also to predict future hazards.
First, laboratory experiments were carried out to understand how the flow of groundwater in offshore sediments can change their geotechnical properties by leaching out the salts in the pores. The MARCAN team discovered that groundwater flow can weaken the sediments and trigger slope failure in submarine sedimentary slopes in a manner similar to that of quick clays onshore. But Aaron Mikalev's team also looked at how offshore groundwater flow may have impacted the seafloor at a much larger scale, this time using numerical simulations of margins with evolving stratigraphy.
Our models with evolving stratigraphy show that offshore groundwater flow is a key driver of pore pressure development and, as a result, of instability in continental margins, particularly in carbonate margins.
The MARCAN team used 3D landscape evolution models to show that offshore groundwater flow can give rise to erosional landforms, with their type, location, and timing being controlled by the depth of the shelf break. To better understand how such erosional landforms evolve, the MARCAN team monitored coastal canyons in Malta and New Zealand. By doing so, they demonstrated for the first time that groundwater seepage can be a main driver of box canyons in limestone. When asking Aaron Mikalev about his personal resume, he is quick to answer.
MARCAN was a fantastic adventure that allowed me to develop both as a scientist but also as an individual, while exploring a fascinating research team of global relevance. And for this unique opportunity, and especially for believing in me, I only have the European Research Council to thank.
The information generated by the MARCAN project has been disseminated as widely as possible. Apart from scientific publications and conference communications, the MARCAN team has organized summer schools and international workshops to develop a new generation of scientists with expertise in offshore hydrology and geomorphology. And the impact is continuing.
The MARCAN project has also inspired new research projects such as MGM to FGR and SWAN, both of which focus on technological development, and Offsource, which is a cost action that brings together stakeholders from across Europe and beyond to find and determine whether offshore groundwater can be used as a sustainable source of potable water in coastal regions.
Offshore Groundwater, Hope and the Hazard, a film about the MARCAN project.